Hi, my name is Abhinav, and this is my Physics 2011 lab for projectile motion. The purpose of this lab is to observe projectile motion and determine the forces acting on the projectile. The purpose is also to compare computational models where one is with drag and one is without drag. The fundamental principles being applied in this lab include constant forces, Newton's second law, and drag. The system of this lab is a paper ball being thrown and the surroundings is the earth and air. By the end of this lab, we will show how the experimental data will show the y component and x component of velocity decreasing due to drag and gravity. The computational model with drag will match this experimental data, and the computational model without the drag will show how the x component of velocity stays constant and the y component of velocity decreases due to just gravity. For my experiment, I threw a paper ball from left to right along a meter stick. The meter stick helps set the initial and final positions for the experiment. Here's the experimental data of my experiment collected using Tracker. On the bottom, the table shows the time elapsed in seconds and the corresponding position of the marker in meters in both the x and y directions. On the top are the graphs showing a visual representation of the data from the table. In order to create the computational models, I first had to do some calculations and add code to GlowScript so that the models would be created as intended from my experiment. I set the initial position to 0, 0, 0 and set the initial velocity to 2.385 to best match my experimental data. I set delta t to 1 over 30 and total time for the loop to be less than 0.567 seconds based on my tracker data. I set b to 0.19 to best match the data as well. To set up the net force calculations, I first calculated the magnitude of velocity squared and v hat. I then updated drag using the equation negative b times v squared times v hat. I updated gravity using the vector 0, negative mg 0, and finally updated the net force by adding the gravity force and drag force together. When updating the velocity and position, I used Newton's second law to update both accordingly. The code and calculations are the same for the both drag and no drag computational models. However, for the no drag model, b is set to 0 instead of 0.19. Here's the resulting computational models with drag. In this model, we will assume that the effects of drag are being perfectly distributed onto the paper ball. As you can see, the trajectory of the paper ball is parabolic, and the velocity decreases in both the x and y direction. The decrease of velocity in the y direction isn't as linear due to the effects of vertical drag on gravity. Here is the resulting computational model without drag. In this model, we are assuming that there is no drag affecting the paper ball. As you can see, the trajectory of this paper ball is still parabolic. However, the velocity in the x direction is constant, and the velocity in the y direction still decreases. The difference is that the paper ball still travels further in the x direction, and the velocity is constant due to drag forces being set to 0, which means that the net force will stay at 0. Here's a comparison of all the models and the data. As you can see, the computational model with drag best represents the experimental data. The computational model without drag overshoots the expected trajectory due to less forces acting against the motion. So some sources of error in this experiment that could result in slight skews in the data include setting the calibration stick exactly in tracker, human error when tracking or recording the projectile motion of the paper ball, and random error when measuring displacement of the ball. So what does it mean? In this lab, terminal velocity wasn't represented by any of the models because the object, or paper ball in this case, never experienced free-falling motion. The experiment that would represent terminal velocity would be if a ball was dropped from a certain height onto the ground because then the object would experience free-falling motion. What if the object was initially thrown straight up with the same initial speed? Well, the object would take longer to return to the ground since drag will only be acting in one direction. This is also proved by the computational model. In conclusion, the goal of this lab was to observe projectile motion of an object using experimental data and computational models. Another goal was to make computational models with and without drag to understand the effects of drag on projectile motion. The findings from this lab is that the computational model with drag more accurately represents the experimental data than the computational model without drag. The differences between the computational model and real-world projectile motion occurred due to the drag being unevenly distributed on the projectile in the real world, which results in slight variation between the two representations. This concludes my lab report. Thank you for watching.